Okay, let's get started. Thursday, we're going to have the midterm exam, and it's going to be online. I'm going to email it to you at 10 in the morning on Thursday, and then you'll email me back your responses by 11:15 on Thursday. There's going to be 10 questions on the exam, and they're going to be very similar to the 10 questions we're going over today in the review. So is everybody comfortable with the exam being on Thursday at 10? All right. Okay, very good. Let's then start with a review. Again, there's going to be 10 questions on the exam, and they're going to be very similar to the 10 questions we're going over today in the review. So let's get started with the first question, and that is define a relation R on set A, which has the elements 3, 5, and 7, and set B that has the elements 15, 16, 17, 18. And that relation is the set of all ordered pairs, X and Y, that are elements of the cross product of A and B, where X and Y are elements of the real numbers, and the relation is that Y divided by X is an integer. So spend 5 minutes or so and come up with your answers to A and B. Okay, let's go over this one. So it says define a relation R on A, and A is the set with the elements 3, 5, and 7, and B has the elements 15, 16, 17, 18, as all ordered pairs X and Y that are elements of the cross product of A and B, where those elements are real numbers such that Y divided by X is an integer. So in A, it asks, is 3R15 part of this relation? And the answer is that yes, it is, because 15 divided by 3 is equal to 5. Then we have is 16, or 3R16, in other words, 16 divided by 3, part of this relation. And the answer there is no, because 16 divided by 3 is not an integer. Then we have a slightly different notation, is the ordered pair 7, 17 an element of this relation? And the answer there is no, because 17 divided by 7 is not an integer. And then we have finally, is the ordered pair 3, 18 an element of this relation? And the answer there is yes, because 18 divided by 3 is 6. Then it asks the question, is R a function from A to B? The answer here is no. There's two conditions for being a function, and this one fails on both conditions. One of the conditions is every element in A must be mapped to something in B, and 7 is element 7 in set A is not related to anything in set B. Then the other aspect of a function is each element in A is related to just one element in B. But if we look at element 3 in A, it's related to 15 and to 18. So it fails on that count as well. That's right, exactly. 318, the ordered pair 318 is an element in the relation because 18 divided by 3 is equal to 6. Okay, let's take a look at the second question. No, this is an ordered the two elements for a function. Yeah, exactly. So the second property is you can't have one element in your domain that maps to two different elements in the codomain. And because 3R15 and 3R18 are in the relation, the element 3 in the domain maps to 15 and 18 in the codomain. Okay. It violates the first property of a function because that states that every element in A must be mapped to some element in the B. And 7 in A is not mapped by this relation to anything in B. In other words, any of those numbers, 15, 16, 17, and 18 divided by 7 is not an integer. And the relation said y divided by x must be an integer. Okay, let's take a look at the second question. Here we see two functions, f and g, that are defined in the real numbers by the following formulas. F of x is equal to x plus 2 times x minus 4, and g of x is equal to x minus 1 squared minus 8. The question is, does function f equal function g? So take a couple of minutes and look at this one, and we'll go over the answer. Okay, let's take a look at this one. So we've got two functions, f and g. F is x plus 2 times x minus 4. So if we do that multiplication, we get x squared plus 2x minus 4x minus 8, and we get x squared minus 2x minus 8 is what f is actually equal to. Then for gx, we've got x minus 1 squared minus 8. Well, x minus 1 squared is going to be x squared minus 2x plus 1. Then, of course, we subtract the 8, and that leaves us with x squared minus 2x minus 7. That is not equal to f. So the two functions are not equal. There we go. Okay. All right, let's go on to the third question. Which of the following is a negation for Bob is tall or John is short? So spend a minute and think about that one, and then we'll go over it. Let's, before we go over question 3, let's go back to question 2 and just consider that for two sets to be equal, they have to have exactly the same elements in the sets. So if I can show that set B has an element that is not in set A, then the two sets are not equal. So obviously, in the case of these two functions, the set of values that satisfy f and the set of values that satisfy g have different values. Okay, now let's go forward to question 3. And the question is, which of the following is a negation for Bob is tall or John is short? Well, remember from De Morgan's theorem that a negation of an or statement is an and statement. And part of that operation is we do the negation of each of the statements or propositions in the or statement. So our negation is going to be Bob is not tall and John is not short. We change the or to an and we negate each of the statements on either side of the or. And in that case, we come up with answer E is the answer to the question. It's the negation of the statement Bob is tall or John is short. E is the right answer. Bob is not tall and John is not short. Okay, let's go on and to question 4. Write the following two statements in symbolic form and determine whether they are logically equivalent. Use a truth table and give an explanation. So the two statements are, if Bill used Python, then Bill did not use a Dorleen cartogram. The second statement is Bill used Python or Bill used a Dorleen cartogram. So take a couple of minutes and go come up with your answers for this, and then we'll go over it. Okay, let's take a look at this one. So we have our two statements. If Bill used Python, then Bill did not use a Dorling cartogram. And then the second statement is Bill used Python or Bill used a Dorling cartogram. So if we let P equals Bill used Python and Q equals Bill did not use Dorling, then the first statement is if P then Q, and the second statement is P or not Q. And these are not logically equivalent. We can demonstrate that by creating a truth table. We have two variables, P and Q. They can take on true or false, so that's going to give us 2 squared or 4 combinations. And we go true, 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 false, false, true, false, false. We take a not Q just as something that is helpful to us to solve the problem. And then not Q becomes false, true, false, true. Then we look at the first statement, if P, then Q, and we get the values true, false, true, true. And then for the second statement, P or not Q, we have P, F, not Q, P true, not Q, F, or false, so that's a true. P is T, not Q is T, so that's a true. P is F, and not P is F, so that's an F. P is F, and not Q is T, and that's a T. We look at the values for if P then Q and P or not Q, they're different with 2 different combinations of values for our variables. So the 2 statements are not logically equivalent. Yeah, I mean, you would have to go through the truth tables to show if they were equivalent or not. But we worked through them exactly the same way that we worked through this particular example. So, you know, and for the various things I'm seeing, we did P then if P then Q and P or not Q. Instead of doing those, you would say if P then not Q and P or Q. So you would do the truth values for those and determine if they were equivalent or not. And likewise, you could say P or Q. Well, Jessica said the same thing as Sebastian. So yeah, you could certainly test that the same way that we tested our the ones that were for this problem. Just a matter of setting up the truth table and seeing what values you get. Okay, let's take a look at the argument form here. And we have if P, then Q or not R. Then we have the minor premise, if Q, then P and R. And then we have the conclusion, if P, then R. So spend a couple of minutes and look at this one, determine whether or not this is a valid argument. And we have a truth table here where the answers, well, the various components are put into premise and conclusion form. So look at that and then make a determination on whether or not it's a valid argument. So take a couple of minutes and look at that. Okay, Jessica, now I see what you were saying. If instead of using Q is equal to Bill did not use a Dorling cartogram, we said Q is equal to Bill used the Dorling cartogram, then just intuitively, it looks like the statements you provided would be equivalent to the ones that we did, except we said Q was Bill did not, you're saying Bill did. But again, just to be on the safe side, I would do a truth table on those. But I think at an intuitive level, yeah, it makes sense. Right, right. So they weren't equivalent. So doing it that other way, we came up with the same answer that we did when we had Q is equal to Bill did not use a Dorling cartogram. Um, it's on our course site under course materials, and you'll see something called reviews, a folder called reviews, and this particular review is in there. Okay, let's take a look at this one. So we have our two premises, if P, then Q or not R, and if Q, then P and R. So there's three variables, P, Q, and R. And so we have and each one of those has two possibilities. So we have 2 to the third, and that gives us 8 possible combinations of truth values. And so we write those out for P, Q, and R. And then we do some intermediate work to get not R, Q or not R, and P and R to make it easier to determine the truth values for the two premises. The two columns where you see blue cells highlighted are the two premises. The first one on the left is the major premise, and then the one on the right is the minor premise. And we highlighted each one of the rows where the two columns had equal truth values for the two premises. So you'll notice in blue, each one of the premises was true. Remember, an argument is valid if the conclusion is true when each of the premises is also true. So we highlight the truth values that result in our two premises being true. In this case, there's 4 of them. And then we determine the truth values for our conclusion, which is if P then R, and see if we get an F as a result. And in fact, we do if P then R for this combination of P is T, Q is F, and R is F. We have the case where P is true and R is false. That gives us a false for that conclusion, but the two premises are true. So the argument is not valid. Okay. The third one is not false because it's vacuously true. P is false on the third one and P is false on the fourth one. And so when the antecedent is false, the conditional statement is vacuously true. Okay. All right, let's now take a look at question 6. Draw the circuit that corresponds to the following Boolean expression: P and Q and not R. No, just you can develop the circuit directly from the Boolean expression. Okay, let's take a look at this one. So we want to draw the circuit that corresponds to the Boolean expression P and Q and not R. And that means we have three inputs, P, Q, and R. So we'll take first the outer logical operator, which is an and we'll put an AND gate into this, our final output signal. So we have an AND gate here. And the two signals going into it are going to be not R, and up here, P and Q. So going from R to not R requires that we have a not gate. And going from P and Q to P and Q requires an AND gate here. And that then is our circuit. P, Q, R, take P, Q, feed it into an AND gate, and we get the P and Q signal. Feed R through a NOT gate, and we get a not R signal. Put them both into the AND gate, and our signal is going to be P and Q and not R. Okay, let's go to the next one. Rewrite the following statement formally. Use variables and include both quantifiers for all and there exist in your answer. And the statement is, all men are mortal beings. Okay, let's take a look at this one. So if we say that a P of X is equal to X is a man and Q of X is equal to X is a mortal, then our statement formally could be written for all X, where X is an element of this universe, if P of X, in other words, X is a man, then Q of X is mortal. Okay, let's go on to the 8th question. Okay. So we have two statements, P of X, X is a man, Q of X is a mortal. Then we would say for all X, such that X is in the universe, if X is a man, then X is a mortal. And I think what she was meaning when she said use both statements is you have the option of using them depending on how you set the, how you solve the problem. In this case, it's a universal and it's just a universal conditional. So it's pretty straightforward for all X, if PX, then QX. But if the nature of the question was a little different, then it would have, maybe the answer would have required using a there exist instead of a for all. Okay. Okay, here we go. Alrighty. Okay, so next question, question 8. Which of the following is a negation for there exists a real number X such that for all real numbers Y, X times Y is greater than 10? So take a few minutes and go over that one. And again, we want to do a negation for this statement. Okay, well, this is an existential statement. So we start with the negation of this existential statement, there exists. And when you take the negation of an existential statement, you get a universal statement for all. And then it's the negation of the premise or predicate of this. And so then we go, once we've taken the negation of there exists and we get a for all, and we go to the next level in, which is for all real numbers. So then we have a negation for all real numbers, and a negation of a for all is there exists. So we've gone from this statement, there exists a number such that for all real numbers, we now have this statement based on the negations. For all real numbers, there exists a real number. And then we take the negation of the statement, in this case, x times y is greater than 10, and the negation of that statement, x times y is greater than 10, is the statement x times y is less than or equal to 10. So looking through the answers, we automatically can scratch off A, B, and C because we know the negation of this existential is going to be a for all. And then we look at the statement E, and it's got y and x mixed up. Statement D looks like the one that we were saying. For all real numbers x, there exists a real number y such that x times y is less than 10. Statement F is not saying the same thing as statement D and saying for all real numbers x and y, rather than once you pick an x, then there exists one particular y. For F, it's like you pick an x and for any y. So we scratch that off. So we scratch E and F off, and that leaves us with D as our answer. Okay, let's go to the ninth question. Let T be the statement. If a real number is greater than 2, then its square is greater than 4. So let's write that out formally, then write the converse of that, and finally write the contrapositive of it. Okay, let's take a look at this one. So formally written out, our statement is for all x in the set of real numbers, if x is greater than 2, then x squared is greater than 4. Then we want to write the converse of that. So the converse, we take the consequent and the antecedent and switch them, and we get if x squared is greater than 4, then x is greater than 2. And then for the contrapositive, we take the negation of the consequent and the negation of the antecedent and switch those. So we get for the contrapositive, for all x, it's an element of the real numbers. If x squared is less than or equal to 4, then x is less than or equal to 2. And let's finally do question 10, the last one. Is the following argument valid or invalid? So for question 9, this is one of those cases where it's an implicit universal conditional. And so it's just when we talk about these type of statements in mathematics, she says that this is known as an implicit universal conditional. So that's how we knew to use the for all x. Okay, and then you're welcome. The last question 10, is this argument valid? All men are mortal beings. Gabriel is not a mortal being, therefore Gabriel is not a man. Okay, so let's look at that one. Take a minute. Okay, yeah, so when writing formally, you can use symbols or you can just, write out the words as well. Either approach is fine. If you do use symbols, make sure you define them, like P of X equals X is a man and Q of X is X equals mortal and so on. Okay, so let's take a look at question 10. And then we'll review again the final. Okay, so we have our major premise for all x that's in the universe. If x is a man, then x is mortal. Then we have an instantiation. Gabriel is not mortal. So we then can conclude Gabriel is not a man, and that is valid because it's modus tollens. We take the negation of the consequent, and that gives us the negation of the antecedent for the particular instantiation, in this case, Gabriel, which I represented with G, and then just the variable anybody was the X. Okay, so we're out of time, but let's go over. It is valid. So it's the form of modus tollens. Modus tollens is the form that this argument takes, and it is valid. So again, let's, Thursday at 10, I will email you the midterm, and then you will email me your answers back on at 11:15 on Thursday. And we got a spring break the following week, and we have, so I'll be seeing you 2 weeks from today. The midterm is open notes. Okay, so again, I'll see you 2 weeks from today, and Thursday is the exam. And I will put 9 back up there. Okay, so there's 9. So, and I've got to head to class. We'll go over 5 really quick. So with 5, we want to determine if an argument is valid. So we've got the major premise, if P then Q or not R, the minor premise, if Q then P and R, and the conclusion, P then R. So we didn't have to create this truth table. It was done for us. But of course, we could easily have done it by just getting all the various combinations of truth values for P, Q, and R. We then go through and get some intermediate work that helps us look at the truth values for our premises. The premises are in these 2 columns where we see blue cells. And the blue cells are those rows where both the premises are true. So you can see true, 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 and true, true. All the others, one of the premises is false. An argument is considered valid if whenever all the premises are true, the conclusion is also true. And we see when we do the truth for the conclusion for those cases where the premises are all true. For this fourth row, we have P is T and R is F, and that makes the conditional if P then R false. So it's not a valid argument because we have the premises true, both true, and the conclusion is false. Okay, so I shall, yes, there'll be a partial credit on the exam. And I'll see you guys in 2 weeks. And I'll mail out that exam on Thursday. Great, you're welcome, bye. Thank you, thank you. See you in 2 weeks, guys. Thank you. All right, bye.